Hello and welcome to our video for topic 2 on net gravitational force. So in the last video we looked at calculating the gravitational force between two objects. In this video we'll look at what happens when we have more than two objects applying a force on a third object. Okay, so that's kind of where we'll cap things as three objects. Now in each situation we're going to assume that two objects are stationary, so they don't have the ability to move, and a third one does. Okay. So we need to really just keep in mind and make sure that we're using the rules of vector addition. So in the following diagram, the masses of object A, B, and C are 10 kilograms, 8 kilograms, and 6 kilograms respectively. Okay. Calculate the net gravitational force on object B. I'd like to just kind of put a star by it or something so I remember. Assume all measurements are made from the centers of the object. Okay, so object C is going to be stationary, meaning it's not going to move. Now, in the real world, if these things were all floating around, that wouldn't be true. But in these situations, we're going to keep them stationary just to make our lives a little bit easier. So B has the ability to move as a result of the forces applied by A and C. Now, remember that gravity is always an attractive force. It never pushes things away. So B is going to be pulled towards C. And at the same time, A is trying to pull B towards itself. So we kind of have a tug of war here. Now, we're going to make an F net statement because we're looking for the net gravitational force. So I'm going to say F net. Now, just like in the earlier sections of our dynamics, we kind of have two choices. One is if you can figure out which is the larger of the two forces, you can put that one first and subtract the other one. If you're not sure, then just make anything to the left negative, anything to the right positive, and if it comes out negative, the net force is to the left, and if it comes out positive, the net force is to the right. That's the method I'm going to use in this one, even though we could figure out which one is larger. Now, lots of times people go, well, the force towards A is going to be larger because it's a bigger mass, but when you compare 6 and 10 kilograms isn't even double of 6. But then let's look at the distance. C is really close. This one's 3 times further. And remember that it's inversely proportional to the radius squared. So 3 times further actually gives you 9 times less force. So we would need 9 times the mass to cancel that out. And we definitely don't have that. So this force is going to be larger. So in the end, my net force should end up heading to the right in the positive direction. And this one is a smaller net force, or smaller gravitational force, sorry. So by doing some of this, I can kind of make sure that my work turns out right. Again, there's tons of calculator errors in this unit. So if you are keeping track of some of these things, you make some estimates ahead of time. Sometimes you can catch some of your marks, or some of your mistakes, sorry. All right, so F net is equal to the force of gravity. Okay, I'm going to say between B and C. And then I'm going to pretend that I couldn't figure out which one was larger. And I'm just going to add the force of gravity between A and B. Okay, so F net is equal to G, mass of B, mass of C, divided by the radius between R and B squared. Okay, and then we have G, mass of A, mass of B, divided by the radius between A and B squared. So just for the interest of time and space, I'm just going to stop writing out the constant. But again, it's 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. And you can find that on your formula sheet. But I'm just going to write G in this video just to keep things moving along a little bit quicker. So mass of B, 8 kilograms. Mass of C, 6 kilograms. And the radius, it needs to be in meters. So 2.5, you divide by 100, and you get 0.025 meters squared. Plus, now I said that anything to the left I'm going to make negative, so I'm just going to throw a negative at the beginning of this. Now, it's not necessarily that G is negative, but just that that whole kind of portion of the equation needs to be negative. So mass of A, 10 kilograms, and 8 kilograms. All divided by 0.075 meters squared. Okay, and again, I'm expecting this thing to come out positive. If it doesn't, I'm going to have to go back and check my calculation. So I'm just going to throw all these into my calculator. Okay, so for this one, I got 5.12256 times 10 to the negative 6 newtons. And for the next one, I get negative 9.4862. Okay, now you wouldn't have to write these steps out. You could hammer this all on your calculator, but I just wanted you to see what each of those numbers are, just in case you're having trouble getting this into your calculator. So those would be your two numbers. So I'm going to now go and add those together. And I get a positive 4.173 times 10 to the negative 6 newtons. So I said in the end my answer should come out to be positive. It did come out to be positive. Looks like two significant digits across the board. So 4.2 times 10 to the negative 6 newtons. And in a situation like this, direction is very important. So I'm going to say to the right. And that would be my final answer for that one. So it's very much so using the formulas from the last unit. I'm just kind of tying them all together now. So in example 2, calculate the net gravitational force on object C in the diagram. So now we're going to say that C is what I'm looking at, and that B is going to be stationary. And so is A. So the net gravitational force on object C, I'm going to switch colors here just so I can kind of add to this. So C is going to be pulled to the left by B, and C is going to be pulled to the left by A. Now these arrows are a little bit misleading because obviously the gravitational force of A is going to be quite weak compared to that of B just because it's so far away, like it's 10 centimeters away from C. Okay, but my F net statement is going to be the force of gravity between A and C plus the force of gravity between B and C. Okay, now we already did one of these. We did B and C up here, so I can actually just kind of poach this number because it's not going to change just because now we're looking at C instead of B. Remember, the force of gravity between the two objects is the same, so that part I'm already going to be done. So this is going to be G, mass of A, mass of C, divided by the radius of AC squared, plus, again, I'm just going to leave that because I already know that number from the last question, but you could recalculate it if you wanted. So G, 10 kilograms. Now this is to the left, so I am going to make it negative. G, 10 kilograms. C is 6 kilograms. Okay, and 7.5 centimeters plus 2.5 centimeters is 10. So in meters, that's 0.1 meters squared. Plus the force of gravity between B and C. I wrote my work down up there, so I know that it's 5.12256 times 10 to the negative 6 newtons, and it's to the left, so we're going to make it negative. So it's just a matter of throwing this all into my calculator. So just give me a second while I do that. All right, and my F net is negative 4.722 times 10 to the negative 6 newtons. So remember, the negative is representative of the direction. So when I go to get my final answer, 4.7 times 10 to the negative 6 newtons. And this time it's going to be to the left since it came out to be negative. So that is my final answer for that one. All right, example 3. So calculate the net gravitational force on object M1. Okay, and M1 is 1.23 kilograms. M2 is 750 grams, so if I divide by that by 1,000, it's 0.75 kilograms. And M3, 900 grams, is going to be 0.9 kilograms. Okay, now, if M1 is the one that can move, and these are my stationary ones. Stationary. Because of M2, this object's going to try and move up. Okay? And because of M3, it's going to try and be pulled to the right. So in the end, we're going to end up with some sort of pull as such. Okay, now to sort this out and to figure this out, what we're going to do is we're going to use vector addition just like we did before. So I'm going to draw a quick vector diagram, and then I'll go into some of the calculations. So there's going to be an upward force, force of gravity between objects 1 and 2. And then there's going to be a pull to the right because of the force of gravity between objects 1 and 3. In the end, this is going to be my F net. That's how I add vectors together. I draw a vector diagram and I find the hypotenuse. And forces are vectors, so I'm also going to need an angle. So what I have to do is I have to set out, I have to find force of gravity between 1 and 2, find the force of gravity between 1 and 3, and then use Pythagorean theorem. So I'll start with 1 and 2. So G, mass of 1, mass of 2, divided by r squared. And that's again going to be the radius between 1 and 2. Okay, so G, 1.23 kilograms. And mass of 2, 0.75 kilograms. And between 1 and 2 is going to be 0.2 meters. Again, centimeters to meters, we divide by 100. So I can throw that into my calculator. And I get 1.538 times 10 to the negative 9 newtons. I'm going to do the same thing for the force of gravity now between 1 and 3. So G, M1, M3, the radius between 1 and 3 squared. Okay. So G, 1.23 kilograms, 0.9 kilograms, and that radius was 10 centimeters, so it's going to be 0.1 meters squared. And that gives me 7.3836 times 10 to the negative 9 newtons. Okay, now I'm going to take a second and just stop and see if this makes sense that the force of gravity between 1 and 3 was greater. So M3 is greater than M2, so that should mean more gravity. And then it's also closer, so that means more gravity as well. So that makes sense. These numbers most likely are correct. It doesn't guarantee it, but it does give them a chance that they'll check out. So looking at my triangle here, I have a squared plus b squared equals c squared. Okay. So I can take my two numbers, put them in. So 1.538 times 10 to the negative 9 newtons squared plus 7.3836 to the negative 9 newtons. So I'm going to square root all this. And again, I'm using all of the decimals in my calculator. So I don't write them all down, but they are there, and I am going to bring them all with. So okay, I'm looking for the hypotenuse. So I should get a number that's definitely bigger than the other two, which I do. So 7.542 times 10 to the negative 9 newtons is equal to C. Or by C, we're like talking about F net. Okay. So I have that portion of my final answer. So well, technically, I guess we're looking at one significant digit here. So this would be 8 times 10 to the negative 9 newtons. But now I need an angle to go with it. So I can do tan theta. So opposite over adjacent. So when I look at how my diagram is drawn, okay, I have the opposite as the force of gravity between 1 and 3. So I can check back on my work because it's all organized. And divide by this one. So I'm going to use the second function of tan to do that, and then I'll put those numbers in. So second function tan, and I'm going to just scroll up my calculator because I want to find where I actually calculated those and grab the whole number if I can. So got that one, and looking for the next one. Perfect. Okay, make sure your calculator's in degree mode, or else you might get some wonky answers out, but 78.23 degrees. So if I had to round that off, that would be 80 degrees. And the way my diagram is drawn, that would be like east of north that we could label that. Okay. You might also, depending how you drew your diagram, if you first drew to the right and then you drew up, you would get the other portion of the angle. So you would end up rounding to 10 degrees north of east, and that would be okay as well. All right, example 4. This is where things get real. Okay, so these questions usually give people a little bit of problems, but the nice thing is that there's really no variation to them. Okay, so they kind of run through the same steps all the time, but it definitely takes a little bit of thought and some mathematical ability to get yourself through these. So two objects, x and y, are placed in a straight line. So I'm going to call this y, this is x. The centers are 16 centimeters apart, so I'm going to call that 0.16 meters. I'm just going to convert that to begin with. Object x is 3 times heavier, so I'm just going to say that this is like 3 times mass, and this is just 1 times mass. You can pick whatever numbers you want. You could say one's 30, one's 10, one could be 300, one's going to be 100. If you can keep one of them as 1, though, it does make your life a little bit easier, and I'll show you why in a few seconds here. So I'm trying to put Z somewhere in between these two so that it experiences a net gravitational force of 0. So what that means is that its pull to the right is going to be the same as its pull to the left. Well, this mass is less, so it has less pull, but I can compensate for that by putting Z a little bit closer to it. So less mass, but also less distance, and things should work out for me. Okay, so I'm going to kind of show you the full mathematical way to do this. You might be able to find a shortcut through here, but I'm going to leave that to you to find. So now I need to look at kind of what these formulas are going to look like. So again, those two pulls, the pull from y and the pull from x, have to cancel each other out. So the force of gravity between x and z has to equal the force of gravity between z and y. That's my first relationship. So I'm going to replace each of these with their formulas. So mass of x, mass of z, and g, mass of y, mass of z, radius of y and z squared. Okay. Now at this point I can cancel out anything that's identical on each side of the formula. So I have a gravitational constant and I have the mass of z. So it actually doesn't matter what the mass of z is, it would get parked in the exact same place. Okay, so just kind of rewriting what I have now. Okay, mass of x and mass of y, I can kind of sub those out. Okay, now I can put this in as we said x was like 3 times the amount of mass as the other one. So I'm going to call this side 3 and this side 1. Now here's the problem. We have two unknown variables that are different from each other. So we have the radius between x and z, the radius between y and z. So that makes them a little bit difficult to solve for. But if we go up here, we can use a little bit of fancier, kind of like just a linear geometry. So if from the center to the center is 0.16, okay, so the center to the center is 0.16. If I call from z to y, if I just call that r, then that makes this side over here 0.16 minus r. So for example, if r is 5, okay, so this section here that I'm coloring in red right now is 5, then the other section has to be 11 because 0.16, I subtract 5 and I get 11. So this is kind of the first catch that's going to help me get through this. Okay, so my radius on this side is going to be 0.16 minus r. Okay, and on this side I've labeled it as just r. Okay, now remember that these are, the radii are squared in these formulas, so if I'm going to label it as 0.16 minus r, that whole thing has to get squared. Now I picked this to be this way, so that way in the next step you'll see what happens. So we're just going to take a quick second and look at an algebra lesson here. Okay, so this is the same thing as AD is equal to BC. So if you think about trying to get rid of the denominators, I would multiply by D, and then I could multiply by D on this side, which puts it on the top, and then I could times by B, which puts it on the top. Okay, so basically when you have two fractions, if you want to get rid of the denominators, just take the denominator and stick it on the numerator on the other side. And that's what I'm going to do right now. So I have 3r squared is equal to 1 times the denominator on the other side. So it's just going to be 0.16 minus r squared. Okay. Now, if this was a math class, you'd be looking at this and you're like, oh boy, chances are I'm going to have to FOIL out that binomial, okay, which isn't going to be super fun. And then I'm going to have to group like terms. I'm going to have a quadratic. I got to solve the quadratic equation. And, you know, you got a whole run around. But we're in physics and we're looking for a decimal answer in the end, or, you know, something numerical. We don't need a fraction or anything like that. So I'm going to show you a shortcut to get yourself out of having to do all that work. So what you're going to do right now is you're going to square root each side. Okay, so the square root of 3 is 1.732. Now there's more decimals I'll keep in my calculator, but for now I'm just going to write that down. So square root of 3 gives me that. The square root of r squared gives me r. And then the square root of everything on the other side, excuse me, is 0.16 minus r. At this point, I'm just solving an algebraic equation. So I'm going to group like terms. I add an r. So I got 1.732 on the left. I add one more. So now I'm just going to write this on the side. I'm kind of running out of space. Oh, I got a little bit more here. So 2.732r, because I added another one to it. It's equal to 0.16. And I need to divide. So 0.16 divided by 2. Gives me r equal to 0.0585 meters. Okay, so this again, if I go back and look at my diagram, this side here was r. So what that tells me, I'm just going to go to 2 significant digits here. There's nothing really measured per se to go off of, so I'll go to 2 significant digits. But it'd be 0.059 meters from y. Now that's enough for a final answer, but just in case the question was to ask you like, well, how far is it from x? Then I would have to go 0.16 minus 0.059. And I would get 0.10 meters from x. Okay, now at this point back here, I'm just going to switch colors. At this point here, again, I took this portion and I assigned it so that I knew it would be opposite with the 1. Okay, doing that just makes life a little bit easier. I've always found, because if you think about it, if you do it the other way and we switch these two, and we have 0.16. When you multiply up, okay, you have 3 onto 0.16 minus r squared is equal to r squared. And then when you square root everything, okay, you get 1.732 to 0.16 minus r is equal to r. You have to distribute. So you're going to have to use distributive property, distribute in. So it's just an extra step. So I just like to do it that way. I kind of have a little bit of a forethought. Now, if you're having a little bit of difficulty with this, that might just lead to confusion. It doesn't really matter. Just call one of them r, one of them 0.16 minus r, whatever the distance is minus r, and solve. All right, so this brings us to our net gravitational force practice. As always, please pause the video, give these a try yourself, and if you're stuck, then you've come to the right place. So question number 1, 3 objects all have a mass of 10 kilograms and they're positioned in a straight line exactly 50 centimeters between each respective center. And you're looking for the net gravitational force on the object in the middle. You'll see that the answer is 0 newtons. If they're all the same mass and they're the same distance apart, the pull is going to be the exact same. So whatever it's pulling the center one to the left is the same as what's going to the right. They're going to cancel out, and the net force is going to be 0. So I'm going to spare calculations, although you could do a calculation if you wanted. I'd recommend that this was a test. Just give it a quick explanation and move on. All right, calculate the net gravitational force, including direction on the object on the far right of the diagram in question 1. So on the far right, it's going to be pulled to the left. I'm going to call this A, B, and C. So it's going to be pulled to the left because of B, and it's going to be pulled to the left because of C. Okay, so I can add those together. Now, it's kind of funny that it says including direction. The answer doesn't have a direction. So I'm here to add that in right now as we work through this. So F net is going to be the force of gravity on A and C plus the force of gravity on B and C. Okay. Now again, you can figure out that this is left, so you could do this all as positives if you want, but I'm going to throw the negative in there, so negative g. And again, I'm not going to, if you skip to this part of the video, I'm not going to write the g out every time just to speed the video up a little bit. But so the mass of A, 10 kilograms. You could write this as 10 kilograms squared if you wanted, but I'll put them both in. And then A to C is 50 centimeters plus 50 centimeters, which is 1 meter. Okay. And then I'm going to add another negative direction one, G, 10 kilograms, 10 kilograms. And this time B and C is only 0.5 meters squared. Okay, now you might be looking at this and you're like, man, I can find some ways to speed this up in my calculator, where I could do some like factoring or whatever. Go right ahead. I'm going to keep trucking along this way though. Okay. So this one gives me negative 6.67 times 10 to the negative 9 newtons. And this one gives me negative 2.668 times 10 to the negative 8 newtons. Okay, and again, you wouldn't have to write those out, but I just wanted them to be there just in case you're having difficulties with the calculator portion of this. And I just have to add these together now. And I got negative 3.335 times 10 to the negative 8 newtons. So I'm going to three significant digits. I would have 3.34 times 10 to the negative 8 newtons, and that would be to the left because my answer came out to be negative. All right, question 3. Using the diagram to the right, determine where you would need to put mass B so to experience a net gravitational force of 0. So I have 5 kilograms and 15 kilograms. Okay, I will solve this using those numbers, but I will say if this was me and I was doing this, I would switch this to 1 and I would switch this to 3. Again, the exact mass doesn't matter. It's just like what is the proportionality to each other. So 15 is 3 times larger than 5. And that just allows you to have a 1, which makes the math a little bit easier. But again, chances are you might not have thought of that or known that you were allowed to do that. So I'll go through this the full way. Okay. Now I like to just kind of, so this is mass A, mass C and S. Where would you put mass B? I like to just kind of visualize this by saying mass B would have to be somewhere closer to the smaller mass. Okay. And I'll assign R and 1 minus R here in a second, although it's not going to matter because both are numbers. So I'm just going to call this R, and this can be 1 minus R. Okay. So again, if you think about if the distance from here to here is say like 30 centimeters, then the distance from the middle to here would be 70 centimeters because the two put together have to add to be 1 meter. So if they have to add, then this one is just basically 1 subtract whatever the other one is. Okay, so the force of gravity between A and B has to equal the force of gravity between B and C. So it's G, mass of A, mass of B, radius between A and B squared, and G, mass of B, mass of C, radius of B and C squared. And so canceling anything out that's the same on each side. Mass of B, mass of B. And if you go back in the video to example 4, I went through a very similar question to this too. So if you're looking at this, you're like, man, I really could have used another example a little bit slower. Check example 4. Okay. So my mass of A is 5. I'm going to ditch the units on this because ultimately it is just like kind of a proportionality type question. So not too worried about the units here at the moment. 15. The radius of between A and B I called R. And between B and C, I called 1 minus R. Okay, make sure that squared ends up on the outside of the brackets. People love to put it on the R, but it's not just the R that's squared. It's the whole 1 subtract R because that is the distance or the expression that you've laid out to describe that distance. So multiplying up, I have 5 onto 1 minus R squared. On this side, I have 15 R squared. Remember the shortcut is to square root everything. Okay, now you can keep writing this as root 5, or you can switch it to a decimal. So I find that people sometimes struggle with the root, so I'm just going to write this as a decimal. Okay, so square root of 5 gives me 2.236 onto 1 minus R. And on this side, square root of 15 gives me 3.87 to R squared. Okay, so again, if this was me, I would just write root 5 and root 15, but I'm trying to make this so that everyone can have a good chance of being successful with it. So I just want to write out what I have here again, where I have some more space. So 2.236, 1 minus r is equal to 3.872 r squared. Okay, so now I need to do distributive property. So it's going to be 2.236 when I multiply by 1 minus 2.236r is equal to, that's not squared anymore because I square rooted it. Let's go in and fix that. Okay. It's equal to 3.872r. Now I'm going to group like terms. I want to keep the r's positive. So I'm going to add these ones to the other side. I'm going to be 6.109 r's. So I'm going to divide 6.109, divide by 6.109. Okay. And I end up getting 0.366 meters is equal to r. Okay, so 0.366 meters equal to r. Go up, look at your diagram. R was the distance between A and B, so 0.366 meters from the 5 kilogram mass. And if you want to know how far it is from C, just go 1 minus r, and you'll have yourself an answer. All right, calculate the net gravitational force, including direction, on object B in the diagram. So because of object C, it's going to try to pull it downwards. And because of object A, it's going to try and pull it to the left. So if I make a free body diagram, what I'm going to have is I'm going to have a force to the left. I'm going to have a force downwards. Again, remember we draw tip to tail. And this right here, this resultant is going to be my F net. And an angle is always going to be important. Okay, so this here is going to be the force of gravity between A and B. And this is going to be the force of gravity between B and C. So I need to come up with both of these numbers right now. So force of gravity between A and B, G, mass of A, mass of B, divided by the radius between A and B squared. So again, I'm just writing the constant as the actual G just to kind of keep things moving along here. So 8.32 times 10 to the 18 kilograms. Okay, and then the radius, make sure it's in meters. It is 3.25 times 10 to the power 9 meters. Before I do the calculator portion, I'm just going to write the next one out, and then that way I can do them both at the same time. So G, mass of B, mass of C, and then the distance between the two of them. So G, 2.76 times 10 to the 17 kilograms. Not sure why that's in the exponent. It shouldn't be. The unit should be down below, but I'm sure we all know that. And the distance between them, 2.14 times 10 to the power of 9. Okay, so calculator time. Again, make sure that you're doing your scientific notation properly. And I forgot a squared symbol on there actually, so let's put that in there right now. Excuse me. Okay, so that was that answer. And then my next one. You know, honestly, normally I would go back and redo each of these calculations if I was on like a test or a quiz quickly, just to make sure I get the same numbers before I do the rest of the work and realize that I messed something up. But we have an answer here at the end, so I can catch mistakes if that's kind of what it comes down to. But now to find my F net, I'm going to do A squared plus B squared equals c squared. So it's going to be those two numbers up there. So squared plus so I can square root each of these sides. And that gives me this number right here. So it looks like it's lining up with the answer key, which is good. Okay, so that's my F net. And then again, you need an angle. So I'm going to use tan theta of those two numbers. So the top one is the force of gravity between A and B. So again, I have things nicely labeled. I can figure out which one's which without guessing. And my bottom one. And we need to use that second function of tangent to find the angle. Okay. And I got theta equal to 6.39. Okay. Which is fine, because that would be the other portion of the angle that would add up to be 90. It's just looking like my angle also is south of west, so we'll have to look at that in a second here, but let's get this all rounded off properly. So we're looking at three significant digits, so I got 1.30 times 10 to the power of 3, 6, 7, 8. And then I have 6.39 degrees. Now, let's just double check here my vector diagram and see what's up. So I did the force of gravity of AB, and then I drew BC, and then I found F net. Okay, so I just want to make sure that I have the right masses and everything in. So for A, I have 8.32, good, 2.76, and I use the right distance. So this number would go here. Okay, and now I can see what I've done wrong already. I put these two in upside down. Okay, so what I would do is I would just go back and recalculate this. But I know that because they're upside down, all I did is I kind of found as if it was drawn like this. So what that does is that makes this west of south. If you flip them around, then you'll get 83.6 south of west. Okay, so that's what I get for talking up my organization and then not writing a formula down. So you can see if you go tan theta, and then you look and you actually do like FG of BC divided by FG of AB, and then you look for those amounts, there'd be less mistakes made. So that's what you get for skipping steps. It happens to the best of us. All right, question 5. Object A, 415 kilograms. Object C, 672. They're 1.23 meters apart. Where would you need to put object B? So we got another one of these questions. Okay, so A and C. So we have 415 kilograms, 672 kilograms. And where am I going to put object B? These are 1.23 meters apart in the centers. I'm going to have to put it somewhere over closer to A. So I'll call this R, and this can be 1.23 minus R. Okay, so hopefully you're starting to get the hang of these a little bit more, but if not, that's okay too. They're a little bit trickier. Okay, so this is going to be G, mass of A, mass of B. This would be G, mass of B, mass of C. Okay. Again, cross out anything that's the same. Notice how the mass of the object in the middle doesn't matter. So the mass of A, 415. Mass of C, 672. And then I said I was calling this one R, so it's R squared. And this one is 1.23 minus R squared. Okay, so multiplying up again, if you kind of don't understand why, just go back and watch the example from the actual class examples in this video. I go through it in a little bit more detail there. So it's going to be 415. And 672 R squared. Again, we have the luxury in math or in physics of going to decimal answers, so I'm just going to square root everything's to the square root of 415. Gives me 20.3715. 0.23 minus r. That's going to be 25.9229 r. Okay, so I need to do distributive property and multiply into both of those. So I'm going to use that whole number in my calculator, like all of the decimals. So I get 25.057 plus, oh, that wouldn't be a plus actually, it would be a subtraction. So let's fix that up, subtract 20.3715 r is equal to 25.9229 r's. Grouping like terms, trying to keep r positive means I add these ones to the other side. Just going to finish this out up over here. So I'm left with 25.057 is equal to, just got to make sure I grab the right numbers here. So I need this one, and I need to add this one to it. So I get 46.2945 r's. So divide and divide. So 25. Let me go back and use the whole number here actually. So grab that one, divide, and I get 0.541 equal to r. Okay, now again, I kind of ditched the units in here just to clean it up, as I find that people really struggle once you start throwing in meters and things like that, because they're like, is this a variable? Is this like a unit? So I generally, in these proportionality ones, try to leave the units out just to clean it up for you a little bit. But in your final answer, you should have a unit. So if I take a look at where I labeled r on my diagram, that was over here. So it's going to be 0.541 meters from A. And again, if you want the distance from C, just go 1.23 minus 0.541 meters, and you'll get 0.689 meters from C. Okay, now again, if you really understand the formula and the proportionalities, there is another way you can get yourself through these. I don't want to call it a shortcut because it still involves quite a bit of thought, but you might be able to kind of play around with, well, if this mass is how many times larger than this mass, what do I have to change the radius by to get that to cancel out the difference and stuff like that. So if you really want to go through that, just pop by some morning and we can go through it together. Other than that, that's everything, and we'll see you all later.